Well, this talk is called Scale Symmetry and its Use in 3D Worlds. It's quite a sort of abstract talk, so not that practical, I guess. And I'm going to explore this topic in the form of a question. What are the basic shapes around us? What are the basic shapes in nature? So, bit of a thinker, that one. So, because that's a bit of a tricky question, let's start with something a bit easier. What do the existing 3D modelling packages think are the basic shapes in nature? I mean, a 3D modelling package is supposed to be modelling things in nature, so what do they think are the basic primitives? This is what Maya thinks. These are a lot of the primitives that it uses, same with Max. And pretty much always with shapes, we define shapes by their symmetries. So if we have a look at them, a cube, you can rotate it by 90 degrees, and again by 90 degrees, so it's got rotational symmetry. The word symmetry just meaning it's the same. So it's the same when you rotate it 90 degrees. The cylinder, you can rotate it any number of degrees around the vertical axis, and you can rotate it 180 degrees around the horizontal axis. So it's got a different sort of rotational symmetry, but still it has some rotational symmetry. You could also say that they've got mirror symmetry. So if you took a horizontal mirror halfway through the cylinder and you reflected the whole thing, it would look the same. So that's why you can say that it's got mirror symmetry. And that's pretty much true of most of these. The sphere's got all sorts of symmetries. Well, you can rotate it by any angle and it looks the same. And you can reflect it around any plane that goes through the middle of it, and it looks the same. So again, it has rotational and mirror symmetry. And that's pretty much true of all of these. We've also got some other symmetries. A plane, if you don't think of it as being a kind of small plane, but an infinite plane, then we can say that if you shift it horizontally, it still looks the same. It's still the same plane. So it's got a translation symmetry. If it was a grid, then you could only translate it by certain fixed values for it to look the same. But either way, a plane or a grid has got translation symmetry. Apart from that, this one's quite an interesting one. If you rotate it and you translate it, then it looks the same. If we're considering a sort of infinite height helix, if you imagine it continuing up and continuing down, then you can define this shape by the fact that if you rotate it a certain amount and lift it a certain amount, it looks the same. So it's actually got a bit of rotation and a bit of translation in its symmetry. You can actually say the same for all of these if you move them away from their origin. So, for example, if you took that cube, if you moved it away from its origin, then rotating it around its origin, it's not the same. But if you rotate it, say by 90 degrees, and then you translate it, it becomes the same. So if this was moved away from its origin, then we would say it has a symmetry which is a rotation plus a translation. Anyway, these are commonly considered to be kind of quite basic shapes, and they've been considered that way for 2,000 years. In fact, I think Euclid came up with it, and they're called Euclidean geometry, various types of Euclidean geometry. And they involve mirror symmetry, rotation symmetry, and translation symmetry. But there's two problems with this kind of view of the basic shapes. The first is, well, where do we actually see these around us? I mean, they don't look very natural. I mean, there's a lot of these around, like the Earth, the Sun, and the Moon. But apart from that, I mean, there's something that's not quite right. And the second problem is, well, they've forgotten a symmetry. Scale symmetry. Right, none of these involve scale symmetry. And it's almost as though people didn't really realise that that mattered up until about 50 years ago. So, what does scale symmetry look like? Well, this is a scale symmetric shape. If you ignore the border around it and imagine it as being sort of infinitely big, then if you scale it up from the centre, you enlarge it by any factor, it'll look the same, so it's scale symmetric. This has got scale symmetry. If you enlarge it by certain amounts, maybe if you multiply it by 2 in its size, this being the centre, then it'll look the same. An infinite cone is scale symmetric, as long as this is the centre. Then enlarge it or shrink it, and it'll be the same shape. So it's got scale symmetry. This shape here is a bit more complicated. If you rotate it a certain amount and scale it, then it looks the same. So its symmetry involves rotation plus a scale. And in fact, there were a couple of other examples we've looked at that do have scale symmetry. Just an infinite plane. You can scale it up, it still looks like a plane. Same with a straight line. They're both actually scale symmetric, though they're kind of boring examples. Alright, so does that help in kind of getting to the root of what the basic shapes available to us are? I guess the next question to answer is, which of those symmetries would we most likely see around us? And the answer's got to be a bit of all of them. I mean, on average, anything that you look at is much more likely to have a bit of all type of symmetry than to be exclusively one or exclusively a combination of just 3 and not the other one. So the result of that is, of course, that most things that you see are going to have some scale symmetry, as well as some rotational, some translational symmetry, if they have symmetries at all. So, what do the shapes look like? What is a shape which is made up of some rotation, some translation, some mirroring, and some scaling at arbitrary amounts? What do they look like? First, some boring examples. A line, well, that actually works. You know, translate it by 5 centimeters, scale it, double it, and mirror it, and it'll still look like the same line. Same for an infinite plane. But those are boring examples. Let's get a bit more interesting. This is called a Koch curve, and it has some scale symmetry, some rotational and translational symmetry. So to explain it, this shape that sort of goes along, up, back down, and across, it's the same thing as if I took this whole shape, squashed it, and rotated it and stuck it here. Right? But it's got other symmetries because it's also the same shape as if I squashed it and stuck it there. And in fact, it's also exactly the same shape as if I squashed the whole thing and stuck it there, or stuck it there.
Or the top middle as well.
Hmm?
Top middle as well, you missed one.
Maybe.
Yeah.
I guess probably is, yeah. Yeah, that's interesting. So, it involves a bit of all of the symmetries. I mean, you can kind of add mirror symmetry into that as well if you want. And what about sort of more 3D example? This is kind of doing kind of the same thing to the plane as this did to the line. As soon as you bend a line, it stops being one of these shapes, unless you make it. I mean, as a smooth curve, it stops being one of these shapes, unless you make it into a shape like this. And the same with the plane. It's very hard to see from this picture, but it's basically the same as this. If you took that shape there and you squashed it and moved it up there and translated it, it's the same shape. Here's another one that's probably a bit easier to see. Take this shape and you squash it down, so you scale it down and you shift it, rotate it onto the side or onto this side, you get the same shape. So people usually call these fractals, but we haven't really got very much further with the question because they're not that natural. I mean, maybe they're possibly a little bit more natural looking. They're not artificially smooth like the original primitives that I showed you. So I'm going to cheat a little bit. Let's just say that we're allowed to randomize the process a little bit. So we get something like this. Here I've just randomized this by, instead of making this bit point up in the middle, you randomize it so sometimes it points down, sometimes it points up. So a simple bit of randomizing, but you could probably randomize it in other ways. And now we're starting to get something that looks a bit more natural. Maybe that might almost work as a coastline, maybe it might almost work as the path that a fly takes as it's buzzing around. Maybe it might also almost work as a kind of crack in the ground. It's looking a bit more natural. Same with this idea. If you randomize it, you get something that looks a lot more like maybe mountainous terrain. That's not the best example. And here, if you randomize the angles that are being used in this particular shape, you get something that, well, definitely looks a lot more natural. Alright, so we're on to something. If we actually make use of all the symmetries, and don't forget about scale symmetry, and we put some randomness in, then we're getting some results that look like things you actually see in the real world. What else do you get? I mean, the number of possibilities of scaling, translating, rotating, mirroring, plus a bit of randomness is very high. The number of shapes is a lot. So what are some of the other shapes that you might be able to get from this? Here are some examples. This is actually a shape that I made in a little program that I'm making, which will be subject to a completely different talk. But this is a sort of spongy type shape. This is called Romanescu broccoli, and it's actually a photo, it's not generated. And hopefully you can see that, well, this one doesn't really have much randomness actually. It's very much akin to the pictures we saw before. If you take this cone shape here and you make it smaller and you rotate it a little bit, then, well, you can put it here, for example. Well, these are kind of river networks viewed from above. The branching pattern looks the same at the small scales as it does at the big scales. This is kind of a bit like what I was talking with Matt about. This is actually computer-generated terrain, and if you look at it, you've got some big craters in the terrain, but you've also got lots of little craters. So you can imagine that you could take this whole shape and reduce it down, and you could see how it would fit in a smaller area. But of course, these are all examples of where randomness has been added as well. A fairly standard fractal mountain generation. A fairly standard fractal cloud generation, which you could do with Perlin noise. Again, this is computer generated, but you can see how this kind of looks like a crack. Sort of spongy shapes you can get. You've got big holes going through them, but also if you look at the smaller detail, you can see the same shapes, but much smaller. And if you zoomed out and looked at a much bigger detail, you'd see the same shapes, but much bigger. This is an actual crystal, and you can see there are big blocks here, but also lots of tiny blocks as well. So you've got translation of blocks, you've got scaling blocks. So there's a lot of symmetries there, it's certainly involving scale symmetry. This is computer generated. The shape of this fern is exactly the same as if you'd reduced its size and rotated it and translated it here, and here, and here, and here. You could take any tiny sub-branch of it and it would look the same as the whole thing. Again, this is computer-generated rock, and it uses the same principles of scale symmetry. So you've got big lumps, but on the big lumps you can see much smaller lumps and dips. Another example would be these sort of scattered rocks. You've got some big rocks, but it basically, the shape of it looks the same as if you had shrunk the whole thing down, and you could place the whole thing just in a smaller section, rotated and translated somewhere else.
Actually, so I was just going to say, it might be worth pointing out that that's band limited as well, that previous one, because you've effectively got, there's no massive boulders and there's no tiny sand, so it's a Gaussian distribution around.
You're right, it's not a very good picture. If I found a better picture, it would indeed have, you would see, well, sand, and a few really huge rocks.
So you could probably pick like an average size there, and then you've got a Gaussian distribution going on.
Yeah, it's not the best picture to demonstrate that. And this is frost on some leaves, and well, you can't see that well, but you can see the principle's about the same as what you have for trees. Every sub-branch of the frost looks like the big piece of frost. So the point of this slide is just to say there's loads of things in nature which follow this pattern. It's a good description of what we see. But that's a lot of shapes, and I guess the original question was, what are the core shapes that you find? Well, to answer it, I don't know, but a while ago I had a go at classifying it, and you can classify it quite reasonably into 5 shapes, and you classify it based on how these shapes connect together, how connected they are. So here we go, 5 basic shapes. A cluster is pretty much what we were looking at with the pebbles. This is maybe a better example, closer to what Matt was saying. Completely separated shapes, but you've got this distribution where you've got a few very large shapes, like this planet here. A lot of rocks of varying size, and then the smaller you look, the more of them there are. So there's another example. This is sort of like a dynamited cliff, and you're going to see a few very large pieces and then a lot of dust and smaller pieces. Yeah, another picture. The next level, a bit more connected, trees. So lightning counts as a tree, and in a sense we're talking about the kind of computer science version of a tree structure, no loops as a structure. This counts as a tree in this classification. A tree is anything which has got lumps, and then the lumps have got smaller lumps on it. So there's a cloud. Each of these bulges sticking out of the cloud has got smaller sub-bulges, which you could think of as sub-branches. It's just a very fat, stubby tree, but the topology is still tree shape. Sponges. Well, these are loops everywhere. You've got holes that water can run right through it. It's at every size you can find holes for that particular size, and the closer you look, you'll still find smaller and smaller holes. That's what I'm calling a sponge. A shell is a very hard one to find good pictures of, but it's basically the opposite of a tree. So where a tree is bulges, with bulges coming off it, a shell is hollows, with hollows coming off it. So this is the bottom side of a leaf. You can almost see it there. You've got this big hollow, and then within it you've got smaller ones, and within that, smaller ones. And there's it's not a very good picture, but in this cave system you get basically the same sort of shapes happening. You can think of it as the opposite of a tree. So if you did a cast of this tree and got rid of the tree, then the shape that you've got left is a shell. And basically the same principle applies to the last one, which is a foam. So a foam is like doing a cast of a cluster and removing the actual stuff in the cluster, and you end up with what I'm calling foam. So it's a solid with enclosed pockets within it. So this is an example. Here's another example, amber with kind of pockets of air in it. So it's basically completely the opposite of a cluster, and as a classification, each type is the opposite of the one vertically above it, and of course the sponge is the opposite of itself. So if you did a cast of this sponge here and you got some acid and got rid of the actual rock and was just left with the cast, it would also look like a sponge. Sort of its self-dual. Anyway, this was just sort of interesting to me because I was trying to work out a way to classify it, so that was my classification. But I want to continue to talk about scale symmetry because that's the main part of this talk. So, how is this actually helpful for games? Well, one of the things I think that's helpful about it for games is that with this view that the standard primitives are kind of the core shapes, it's very hard to create something natural looking because how are you supposed to create a tree or a scree slope or something just when your modelling package is working with boxes and spheres and cylinders and core shapes like that don't involve any scale symmetry. So my thought was, well, it'd be nice if we can make an add-on to a package that that allows you to create shapes like these just with a few parameters. And that's something that I made an add-on for a package called Art of Illusion. I'm not going to go into the details of it now. I mean, that might be interesting for another talk. But here are some of the shapes that I made with it. That being a cluster shape, this being a tree shape. And because it's a modelling package, once you've made the geometry, you can light it and colour it in any way you like. This being a sponge shape, and this is a kind of thicker version of the sponge shape. This is also kind of sponge shape as well. It's supposed to be, if you imagine just a load of rocks on top of each other, all touching each other, it just happens to be cut away to make it look a bit less natural. And that's supposed to be a foam. Alright, so that's all well and good, but in games we don't just care about static objects, we want things that move, and how do we know what are the interesting shapes that are animating shapes. So it's kind of the next level to think beyond static and think, well, what kind of different types of moving shapes are there? So let's have a look at it kind of along the same lines as we built up the static shapes. So that's a moving shape. If you look at the kind of translation of it with time, it might look a little bit like this as a graph. So you could say, as a shape, this shape has got mirror symmetry in time, because you can time reverse it and it will look like the same moving shape. Thanks to GIF library about this. And that might look like that. Its translation, or maybe even its scale over time. You get a graph like that. And you could say, well, that's got translation symmetry in time. In fact, the fact that it's got translation symmetry in time is what allows us to make a looping GIF, really. And here's another one. So this has got scale symmetry in time. As long as it was 0 in size at time 0, then you can scale time, if that makes sense. You can, as long as you scale time and scale your spatial scales by the same amount, then you can kind of think of it on this graph, that if you took this graph and you just scale the whole thing up, then this line's not going to move, so it's got scale symmetry in time. Again, if we're following the same line of thought, which ones are we most likely to see? Well, the answer's got to be a bit of all three. Those will be the most interesting, most natural looking ones with some arbitrary amount of all three in them. So I'll just show you a few examples that I've built to demonstrate the types of shapes you get when you have all of the symmetries in space, and you're also using all of these symmetries in time. Right, so we're taking the kind of shapes you saw before, the fractal shapes, but also allowing scale symmetry in time. So I will just start with an example of a fractal shape that doesn't have scale symmetry in time. So we've just got a sine wave operating on this tree. So spatially it kind of looks a bit like a tree or a plant. In terms of its dynamics of how it moves, I don't know what you guys think, but to me that looks quite artificial. And that doesn't have any scale symmetry, it's just a sine wave, so it's got translation symmetry. So what happens if we take that same shape and we apply scale symmetry as well as translation symmetry? So basically what we're doing here is saying, if this tree is the same as the squashed down version of this tree here, then if this tree moves slowly over a period of time, then not only are we going to squash down the size of the tree to make a sub-branch, but we're going to squash down the time so it moves more quickly. And you get something that looks more like this. Kind of looks a bit more like it's bristling in the wind or something like that. And maybe let's extend that to something that looks a bit, well, just a few more branches basically, and this is a 3D version. And, well, I think that looks a lot more natural than the original tree that we're looking at. Quite a strong kind of gusty wind going on there. Here's another example of something with scale, symmetry and time as well as space. I mean, it looks like a load of planets orbiting, right? And this planet's got a moon, and this moon's got little sub-moons. But really, it's a very symmetric shape. You're just building it up of a few symmetries. This whole shape can be translated, rotated, scaled down in time, and you get, and that equals the original one, right? It's made out of symmetries. I don't know how I can replay it from here.
F5, I think.
Might do it from the start.
Oh, do a quick recap.
Yeah, recap for you. Okay, so once we've got all these symmetries happening in space and time, there's a few examples there that show that you can get something that looks quite natural, which could be useful. Well, it could be useful for 3D worlds. I'll finish off this section. There's a very small section afterwards, but I'll finish off this section by saying there's another interesting property of this, which is that, for example, if you took that tree, the very first frame of the tree may look very artificial because you've just got something that's spatially symmetric. You might, for example, the tree might have two branches that come off and then it repeats itself, and you can see that it's quite unnatural looking and very symmetric looking. But since we've got this symmetry in time, and as you remember the tree bristling around, as soon as you move away from time zero and you get to an arbitrary point in time, the tree looks like it's got a lot of randomness in its shape. You know, the different branches could be at any angle compared to where they were at the start. And in fact, if you took an example of that tree or those orbiting planets at a random point in time, it would appear as though we were actually looking at a fractal that's got randomness added to it. It appears to be random. So the same thing could be said of any of these moving fractals, is that you can take something very symmetric at the start, and just by the fact that you've picked a random time to look at it, it looks like it's randomized. It looks more natural as well. And so, in fact, a few slides back where I just added some randomness to make it look more natural, you don't need to add randomness. If it's a moving fractal, then that's already there, that's already taken care of. So very natural, rough, random shapes that we see around us every day are actually very symmetric objects, or you can simulate them with very symmetric objects. And that's good for computer games because we're talking about something that looks very natural coming from something that's very simple to define. Slightly different topic now. Why is scale symmetry? Well, in what other way is going to be useful for 3D worlds, for making computer games? I think I've sort of already covered the fact that it's a good way to build and define natural objects. But another reason why it's very, very useful for 3D worlds is because basically the problem of visualizing and simulating a 3D world is a scale symmetric problem. the fact that we've got perspective makes it a scale symmetric problem. If this is a person standing here and this is their eye, then this is the world that you see through the computer screen, right? This is the frustum. And the problem of rendering the world is kind of a scale symmetric one, because you need to render the world up close, up here, just as much as you need to render the world far away. And if, for example, you take any measure like the number of pixels, if these little points were the number of pixels, then you've basically just got to scaling down these number of pixels to any point along here, and they're equally important. So you've kind of got a symmetry of sorts happening here. And that's quite a big range that's true for. I mean, you may be wanting to see your hand waving in front of your face and also be able to see the mountain in the distance. It's a huge range you've got to cover, but each distance is sort of equally important. So there's a kind of symmetry of algorithms. You want your algorithms to work the same at each scale level. This is an example of a flag. If you're rendering the flag, then you're going to need a lot more polygons when it's close than when you're far away. But also, if you're simulating a flag, you may only need to approximate it by 4 points if it's a long way away. And as you get closer, you're going to want to simulate it with a lot more detail up close. So spatially, there's scale symmetry, but also there's a need for time scale symmetry as well, because if you're simulating these flags, we've got a problem. Most people seem to think it's okay, but it's not really. Imagine making a game and you've got a flag simulator and you decide to reduce the level of detail in the simulation as you get further away. That's fine. That, if you go twice as far away, then you have half as much detail in each axis in the flag. So that means that this part, it means that this flag takes less time to simulate than this flag, which is what you want. But actually it doesn't fix the problem of simulating a 3D world, because even though this takes up less time, there's more space for them in these larger detail levels, in these larger spaces than close up. So, for example, if this flag is only needs only a quarter the amount of detail as this one, well, actually, this distance range is going to have four times as much space for there to be flags. And if we're not talking about flags, we're talking about something like simulating water or something like that, then you find that every time you double the distance, you're using less simulation power per cubic meter, but you've got more of it as you're doubling the distance each time. So effectively, every time you double the distance, you're adding a fixed cost. Right? So at some point, it's unlimited, the cost is unlimited, at some point you're going to run out of CPU time. Fortunately, if you consider timescale symmetry, then, if you work on the fact that you're going to use timescale symmetry, then you're working with the principle that much bigger objects simulate much slower. So with the timescale symmetry which I showed before, the smaller branches of the tree are moving much faster, the big boughs of the tree are moving much slower. And this is kind of seen in the real world. For example, you know, when a person's walking, they may walk with a pace of a repeat cycle every 1 second, whereas an elephant it might be every 2 seconds, and a palm tree swaying it might be every 4 seconds that it actually finishes. And as you get to bigger objects, the actual speed at which they change is less. So if you use this timescale symmetry, then not only are you using a lower resolution in the distance, but you're using a lower time resolution in the distance. And the result of that is that your actual total cost is going to be, you know, C plus half C plus a quarter C plus an eighth C. So it's actually limited. The total all the way to infinity is a fixed amount. So that's actually quite a good way to go, because it's a way to actually take on the problem of a 3D world and find a kind of a clean solution to it, rather than just saying at some point in the distance, well, everything gets fogged. We're using an environment map, and that's it. Alright, well, I'll finish off by showing you a couple of videos that make use of these type of objects. I guess we can call the static ones fractals and the moving ones dynamic fractals, to give them some names. You might have seen some of these before. The water is a dynamic fractal. Big waves, much smaller waves, move much faster. So the water already is one of these objects. And this sort of, I don't know what this is, an iceberg or something. Well, they're static fractals. So they're built by taking an object, then cutting away a few big holes, and then cutting away lots of much smaller holes. And because they're built as these scale symmetric objects, you can view them at any distance. That's why he's able to zoom a long way out and zoom very close. And you've got a symmetry of how fast it takes. It doesn't all chug and go really slowly when you're zooming out. And I'll just show you another one. So I think this is a bit of a new trend. For a long time, people have just fogged things out in environment maps beyond a certain distance, and there's more of an interest in actually having games where you can have an entire world that you can zoom right down into, you can fly into, and this is what this guy's going to do. And the reason they're able to do this is because they're modelling using scale symmetry.
Is this dynamically generated, or is it streamed in from some sort of data? Pre-generated data?
This is a bit of both. There's actually quite a lot of just hard data used, but you can't store every square centimetre with data, so at the very highest level it's using data, and then once you're getting to this sort of level here, the rest is filled in by using fractal shapes. So this is fractal landscape, and if you, I don't know how to do that buffering is here, but once you get a bit further, you can actually see, you can go right down to kind of the meter level and you can still see there are bumps. So there's the same amount of detail at each scale level, that's why it's scale symmetric. And if they'd actually put some clouds in, then you can, we've already seen you can do clouds in quite a similar way. Anyway, yeah, that's it. If you've got any questions, then I should have said at the start you can ask a question as we go along if you want. I forgot.
Tell us a bit about your plugin.
I
think you told me a little bit before, but it sounds like you've gone a little further on it than I thought you had.
Yeah. So the classification that I showed you that had these 5 types.
Yeah.
You can actually extend that with a bit more. It's got a bit more depth to it. So it's got 5 basic types, but when you actually work it out, those basic types are going to be expanded into like 15 specific types. And so we've got these basic shapes, and the idea of this plugin was, well, if these are the kind of core shapes that you find that are natural looking, then why don't we use those as primitives instead of always using cones and boxes as primitives? And so the idea of the plugin is that with a reasonably small amount of parameters, you can change between any of these different shapes. In fact, you can have sliders that will go between any of those. So you can have a cluster, and you can say, well, actually, I want it to be a bit more like a tree. And you might have seen that there was a very thin-looking sponge and then a much fatter-looking sponge. So you've got another slider that you can just say, oh, that should be a bit fatter. And yeah, so that was the idea of it. But it's too much to go in for a small talk. But I should do it then sometime.
What kind of, well, like, how much control did you give over the generation in terms of, because obviously you've given like a fatness control and things like that. But, well, I think you've even shown yourself in your talk. I think what I've started to think this stuff is where it gets interesting is when you sort of can layer this stuff up. So you can generate a fractal terrain, and then can you put your foam over the top of the fractal terrain, if that makes sense? Generate the foam on the terrain or something, on a surface or a manifold.
Well, in the case of the one that I did, this was basically a plugin which generated, what do they call them? It kind of generated Bezier trimesh. So if you, for example, made a sponge, maybe I'll go back to the picture of them. If you made a sponge like that, then it actually, the plugin generated a trimesh for it, but it's a Bezier trimesh, so as you zoom in, it's curved, it's effectively curved. So you, so it's made out of curved patches. So since it is just a normal, once you've made it, it's just a normal trimesh. So you can use whatever you're wanting, other things your modeling tools have got to build onto it. You can, in this particular package, which is Artificial Illusion, you can do interesting things like take any mesh and apply your own height field to it to add. If you wanted to make this not smooth, but a rough surface, then you can kind of layer things a bit like that. And they've actually got their own texture generation system, which is kind of along the same lines. You can generate Perlin noise textures and fractal textures that you can apply to apply on top as well.
Are you using Perlin noise in these? Because you've noised these.
What in the textures?
Well, just in your geometry generation. Well,
No.
you've got some.
No, it's
There's some randomness in there, right?
yeah, but it's very small amounts. The way this particular plugin works is it's easy to show with this. You make, all you do is you put down a sphere, and then you put like 3 or 4 or 5 smaller spheres near it, and it uses that as a seed. And it says, from my base sphere, how did I get to the smaller one? Now repeat that. And so basically, you're effectively, for example, with the tree, you're making the cell of the tree. You're saying the tree trunk is here, the 3 boughs are here, here, and here, and then you turn on the plugin and you go up to detail, and it will do the same thing to each of the boughs to make that into a tree. So
but like
you just have a little.
each time you branch, you're randomising the scale. Is that right?
No, the only thing that's random is when you first make that seed. You say, here's the base, and here's the 3 random bow positions.
Oh, I see. And those 3 are randomised, and so therefore that gets repeated.
They're not randomised. You can put them anywhere you like. If you put them in very symmetric sort of positions, all down one plane, then you'll get a kind of planar thing coming out. So it's only that initial choice of orientations for the kind of the 3 or 4 children that you go for that causes it to look random.
Okay, so I thought you had. Like if you go back a couple of slides to where you had you had the L system tree, I think. Yeah, and so the lower one there. So is that's the same? Is it that's a repeating scale choice for each branch, or is that because I thought that when I first saw that I thought they were randomised scales.
Well, I don't know because I just got this off the internet.
Oh, okay, right.
It looks kind of yeah. I think they've actually all they've done is they've randomised the initial translations.
Yeah,
so it's not as symmetric
and
as this one.
And the thing that got me, I think, is actually I'm just looking out. They've mirrored it in some. They've mirrored the scale randomisation, I think, by look on the branches in some of them. So they've flipped occasionally. Yeah.
Anyway, I think I've gone over my 30 minutes.